so just let us know when it's going.
Yeah, it's recording.
Hello, welcome to the first I Love Chemistry with Dr. Winchester for the year 13. So we're talking about reaction mechanisms today. We're going to do nucleophilic addition to start off with. So, nucleophilic addition. Right in with any spelling mistakes. So, nucleophilic addition, we must have a nucleophile adding to something. Okay, so whenever you look at the overall, you think, what I've done is I've added something to a molecule, and it was a nucleophile attack first. We're going to call it nucleophilic addition. We're going to go over the 3 examples. The first one, let me just check. The first one, I'm just going to give you like a general what happens, and we're going to call the nucleophile nu. We're going to give it a lone pair, because all nucleophiles must have a lone pair, and we're going to say it's a negatively charged lone pair nucleophile. Not all nucleophiles have to be negatively charged. And we're going to have it adding, and these nucleophiles, they normally add over a carbonyl group. So we're just going to go carbon to oxygen, and we're just going to say 2 R groups here, just to keep them, because the general one we don't want to go into too much specifics. So we have a nucleophile, and we're going to add it over this double bond. Okay. So first of all, we need to think, why would this attack this? We know this is a nucleophile, because it's called nu, but if normally we would have to spot whether it's a nucleophile. We'd say anything with a lone pair, that could be a nucleophile, especially if it's negatively charged, even looking better at being a nucleophile. Okay, so you should have some nucleophiles in your head, Cl minus, OH minus, lots and lots of things. Okay. Now, this molecule, before you do anything, you should always think, how is this going to react? We're talking mechanisms, so you need to know where the electrons are, how they're being sucked away or given to any different bit. This carbon is less electronegative than this oxygen. The oxygen sucks the electrons away, so it would become a delta negative, slightly negatively charged, because it's got slightly more of the electrons in these bonds than the carbon. Carbon is going to be delta positive. So now we've kind of primed ourselves to do our reaction mechanisms. You can't forget to write them onto your electrophile as it is. This is going to be an electrophilic centre because it's positive, slightly positive. So our nucleophile, which is negative and got electrons in its lone pair, is going to attack the electrophilic centre of this, which is the positive, slightly positive carbon atom here. Whenever we're doing arrows, we always talk about where the electrons are going. The electrons are starting here, and we have a curly arrow, and they attack a positive atom. Okay, electrons, if they're will attack the atom in the first thing. Okay, and then they're going to make a bond between the nucleophile and that carbon. This carbon cannot have 5 things bonded to it, so one bond must break. The bond that breaks is this oxygen to carbon double bond, and that's okay because the oxygen wants the electrons. It's very electronegative anyway, and we know oxygen's used to having lone pairs on. It's not the end of the world. Okay. The electrons are coming from the bond, so I draw it from the centre of the bond to the oxygen atom. Okay, so we're very precise about where that goes. That's it. That's the first step done. We don't add any other steps. Think about what's going to happen next. That's the first step done. Arrow like we normally do to show reactants to products. Here we just draw out. Start from the carbon, because that's the stuff we've done everything to. So I'm going to draw the carbon in the middle. It's going to have 1, 2, 3, 4 groups coming off it. So we know that's good. That's how much a carbon should have off it. Unless it's a carbocation, it's got positive charge or something like that. Nucleophile has now added there. Okay. We have R group there and an R group there. These 2 R groups stuck up a little bit. Okay. Remember, we're not drawing in 3D, so don't worry too much about what happens. And the oxygen at the top. Now, very careful. This oxygen now has 1 extra lone pair. So actually it used to have 2 lone pairs. Now it has 3 lone pairs, so 1 extra lone pair, because that pair of electrons that used to be in the bond has gone up to the oxygen. If it's got extra electron there, it used to have this electron, it used to share this pair with this carbon, so it used to basically have 1 of them in a way. Now it has 2 of them, that's 1 extra electron, so it's a negatively charged. This thing used to be negatively charged, had both of the electrons to itself, now it's sharing them 1 each in a way through a covalent bond with the carbon. So it's lost its negative charge, it's kind of given it to the molecule, so now this is uncharged here. If we look overall, we want to balance an equation in the number of atoms. Well, the number of atoms is the same, and the charge 1 minus overall, 1 minus overall, so we've balanced it in charge. Good. We're really there, closely there for the last stage now. Now this kind of reaction will always be done in acidic media, so it means that there must be what present? Must be a hydrogen ion present. So there's a H plus present around, and what the last little step is one of these lone pairs, doesn't have to be the one that broke, any one of these lone pairs will attack with positive hydrogen electrons going from where they are, which is a lone pair, maybe a negative atom, but a lone pair, to an electrophile, a positive sensor. Okay, it might be slightly positive in this case it's fully positive. There, it's just going to form a bond, this plus and minus are going to cancel each other out to make something neutral, and we're just going to form an alcohol there, and with whatever our nucleophile was there. So at the end, just one step at a time, don't try and think about anything else happen, or that's the last step anyway. We're just going to have an alcohol, so draw it out, always draw out every step. Don't leave it there, or else you haven't shown what the product is. It's got your nucleophile, whatever it was there, it's got your OH there, that bond goes to the oxygen, not the hydrogen, be careful there, don't stick it in between the OH, that bond is going to the oxygen, and that's nothing, okay? Really, if we were going to have the whole being balanced, we would just have a H plus there swimming around. Doesn't do anything until this step, but then you can see that every stage now is balanced as far as atoms and charge goes. So that's your general nucleophilic substitution. So the next thing we're going to go on to just a couple of examples. Okay, so our first example is going to be the nucleophilic addition reaction of hydrogen cyanide on a ketone or an aldehyde or a carbonyl of some sort. Okay. So we start off with, let's have propanone, so CH3COCH3, and we're going to be adding hydrogen cyanide to it. Now if I ever see in an exam script hydrogen cyanide and I'm asked to do a mechanism, I ignore the H plus for the start. I know that hydrogen cyanide in water will break down, will dissolve and make H plus ion and a Cn minus ion, and the lone pair of electrons we're interested in will be on the carbon. Okay, negative charge and the lone pair of electrons on the carbon, and that's the bit that's going to attack. Okay, this H plus will come in to use later, but we're very important that we don't want to start writing it as HCN, or then we have to break bonds and do extra stuff. When it's dissolved in water, these things dissociate and make hydrogen cyanide aqueous. Cn minus, completely separate from the H plus ion. Okay, first of all, we need to kind of think about what things are. This, to me, looks like a nucleophile, because it's got a lone pair of electrons and a negative charge. Lovely. This thing, we need to think about where its electrons are in this thing. Okay, where's our electronegative atom? It's the oxygen, that's going to suck electrons away and become delta negative. It's taking the electrons away from the bond that it's joined to, so it's taking electrons away from the carbon to make it delta positive, so slightly positive. Okay, just going to swap pens. So, slightly positive, this will be an electrophilic centre. Negative lone pairs, it's a nucleophile. Nucleophile attracts electrophile. So, nucleophile, the electrons come from this lone pair to the carbon. This carbon can't have 5 bonds, so one of them has to break. The carbon to oxygen bond breaks, goes from the bond to the oxygen. Now, we draw it out from the central atom. Very careful. The next thing that you could go wrong here is to draw this out wrong. Don't think about what's going to happen next until you've got it drawn out correctly. Carbon in the centre. CH3 on that side. That's CH3 on that side. This nucleophile has come in here. We've made a bond between the carbon and the carbon. So carbon there. So the bond is there, and then the nitrogen there. It used to be negative charge because both of the electrons are on the carbon. Now it's sharing one of the electrons in this bond, so it's now no charge there. On here we have a single bond, because we've broken one of the bonds, to an oxygen. The oxygen now has one of the electrons, one of the bonds has gone completely to the oxygen, leaving an extra lone pair, actually it's the lone pair, but an extra lone pair on the oxygen, and it's overall negatively charged, because those electrons that it was sharing are now completely on the oxygen, so it's feeling one extra electron, so it's negatively charged. Okay. So we're nearly there. We just remember that we've got this H plus here, and often if it's ever in acid, you've got H plus if you want it. So let's have this H plus chilling over here. Now, this is negatively charged with a lone pair, so it's a nucleophile, so it's going to attack an electrophile. So our last step is the electrons from the lone pair, they attack the hydrogen, which is positive, to form an alcohol with a nitrile on the same carbon as the alcohol. Okay, so let's just draw it out very carefully, and then let's have a look at what the product is and just talk a little bit about why we would use this reaction, and because there's one very specific kind of reason that we use this reaction really. Okay, so let's draw this out. We draw it exactly the same, but now we've got a bond between the oxygen and hydrogen. Okay, so the carbon's in the middle. We say we have a bond between the oxygen and hydrogen. That bond, though, definitely still goes to the oxygen. Now we have CH3 there, CH3 there, and your cyanide down there. Okay. Why we use this in organic chemistry often, and kind of a hint for if you're ever looking at a reaction scheme and you see that a carbon chain has gone one bigger, this is a good mechanism for adding carbons into carbon chains. Okay? What you can do is this nucleophile has got its nucleophilic center on the carbon, so we can use this to add an extra carbon to this chain. Okay, so here you can see there's 2 carbons there, now it's 3 carbons there long. Okay? Overall, the longest chain is still 3 because you've got 3 there in this molecule, but there could be an example where you're stubbing it on the end of a carbon chain and it makes the longest carbon chain one bigger, so you have to think about that when you're naming it. Okay? So this kind of reaction can be used to lengthen the length of the carbon chain. Okay? So our next mechanism we're going to do is exactly the same mechanism, but it's also the same mechanism as when we reduce carbonyls with sodium tetraborohydride.